Welcome back. Today we're going to talk about organometallic chemistry. The required reading is in chapter 13. We're going to focus on the first four sub-chapters in this lecture. In the next video lecture, we're going to discuss the rest of chapter 13. Our objectives are the following. We're going to discuss briefly the naming and types of common ligands in organometallic chemistry. We're going to spend a bit more time on the 18 electron rule and the 16 electron rules. We're going to go over some exercise together. And finally, we're going to spend a bit time on carbonyl complexes, discussing their synthesis, bonding, and IR spectroscopy. All right, so we have learned a lot about coordination complexes. Organometallic compounds basically are a special kind of coordination complex in that they always contain one or more metal-carbon bond. And this metal-carbon bond basically is formed due to the presence of ligands using carbon atom to form coordination interaction with the metal. Okay. So all the naming rules we have learned in coordination chemistry still applies here. The only exception is that, well, not really exception, the only difference is that the kinds of ligands we're going to encounter here is going to be very different from the case of coordination complexes. For example, the most common ligands we're going to encounter are the carbonyl, the carbene, which is CH2 with two free electrons. We're going to encounter a lot of pi systems acting as ligands. For example, cyclopropanol, cyclopentadienyl, pi allyl, which is three carbon atoms each using its free pi orbital, forming a 3-electron pi system. And in some cases, even free molecules such as ethylene and even benzene can act as ligands in forming organometallic compounds. Another common thing that we do not encounter very much in coordination complex, but very often in organometallic compounds is that a lot of pi ligands can behave in a number of different ways. They can use either 1, 2, 3, 4, or 5 different carbon atoms to form bonds with the metal, even for the same ligand. Okay, and we're going to use eta to indicate the number of atoms coordinated with the metal. So eta 1 is going to be called as monohaptal. So if you have cyclopentadiene using one carbon atom to form coordination bond with the metal, shown as in the bottom left, we're going to call it monohaptal cyclopentadienyl. Alternatively, the exact same ligand can choose to use 5 carbon atoms to interact with the metal instead. In that case, we're going to call it pentahaptal, so pentahaptal cyclopentadienyl. And you may recognize this is the more familiar CP-REN we have encountered in ferrocene. Okay. The second major feature that we actually encountered in our coordination complex is the bridging ligand. Here is actually more often. So the symbol for indicating bridging ligand is the same as we used in the coordination complex, which is mu. So mu2 means the ligand, the one ligand interacts with two metal centers at the same time. And in this case, the two metal centers share the same lone pair from the ligand. All right, with that, we're going to discuss the 18 electron rule. This is an empirical rule that applies to a lot of organometallic compounds. It basically says that most organometallic compounds likes to reach 18 electrons in their valence shell. So you may find this is similar to the octet rule we have encountered before. But the difference is that in this case, we're dealing with the organometallic compound, so transition metal atoms are involved. So the way to count the number of electrons in the valence shell is slightly different. Now in the text, there are two ways are introduced to count the number of electrons, and I'd recommend using the so-called neutral ligand method. In this case, you assume all ligands and metal are charge neutral. So this is slightly different from the coordination complex we have encountered before. But it will make it easier because you don't have to deal with the charge state of the metal, and I think it will give less confusion when you look at a very complicated complex. All right, having said that, what you do is you, again, treat the metal as a neutral atom, and then you include all the d electrons in the n-1 shell, and also the s electrons in the n shell. N is the largest number of valence shell in the atom. So basically what this means is that you simply look at which column the metal is in and simply include, simply use the number of the column, and that column number is equivalent to the total number of n-1d and ns electrons on the metal. All right, once you have done that, then you look at the contribution from the ligands. In this case, you again assume the ligands are neutral. So if you have fluorine, chlorine, bromine, iodine, and things like this, they will contribute only one electron instead of two, okay? Because if they are neutral, then they can form basically covalent bond with the metal, and that's equivalent to contributing one electron to the metal. There are other ligands that are normally neutral by itself, such as carbonyl, such as phosphine, such as carbene or carbon-carbon double bonds, and in those cases they will contribute 2 electrons. Then there are those polydentate ligands, monohaptal, trihaptal, things like this. In this case, those ligands will contribute n number of electrons depending on how many number of carbon atoms they have to interact with the central metal atom. And finally, you'll find a lot of cases where there's metal-metal bond. In this case, a single metal-metal bond will contribute 1 electron. A double bond contributes 2, triple bond contributes 3, so on and so forth. Okay. All right, so with that, we can look at a couple of examples on the bottom. Let's see on the left, there's chromium dibenzene. Now, chromium is on column number 6, and the benzene, each benzene molecule uses 6 of its carbon atoms to interact with the chromium. So to count the number of electrons here, it will be 6 plus 6 plus 6, so that's a total of 18. Okay, so move on to the ferrocene in the middle. In this case, iron, assuming it's charge neutral, is on column 8, and each CP ring, cyclopentadienyl ring, use 5 carbon atoms to interact with the metal. Again, assuming it's charge neutral, then it will contribute 5 electrons. So 2 rings will contribute 10. So 10 plus 8, again, that's 18. All right, now on the right-hand side, I have listed 4 more molecules, and I'd like you to pause the video for now and give yourself 2 minutes or 3 to count the number of electrons in all those complexes. All right, and once you're done, you can resume the video, and we're going to go over them together. All right, now let's look at chromium hexacarbonyl. So in this case, chromium is again at column 6, so that's 6 electrons from the metal. each carbonyl is a sigma donor, and usually carbonyl is charge neutral by itself. So each one contributes 2 electrons. So 6 of them contribute 12. 12 plus 6, that's 18. Okay. Manganese, there's a chlorine, there's 5 carbonyls. Manganese is in column 7, and chlorine, assuming charge neutral, contributes 1. So 7 plus 1, so that's 8. And then on the carbonyl side, each one contributes 2, and 5 of them, so that's 10, so total of 18. The 2 molecules on the bottom, so iron, tetracarbonyl, 2 minus. Okay, so in this case, you have to include the charge. Now, iron is column 8 and 4 carbonyls, so that's 8. So that's 16, and then there's 2 minus charge, so 2 additional electrons. So that contributes 2 more, so 16 plus 2, so again, that's 18. And the last one, rhenium, pentacarbonyl, and then there's a phosphine, and then there's a positive charge. Rhenium is column 7, so that's 7 electrons to begin with. You have 6 charge neutral ligands, each contributes 2, and so that's a total of 12. 12 plus 7, that's 19. But because there's a positive charge, you have to subtract 1 electron from the total count, so 19 minus 1, so that's 18. So in all those 6 examples, we have 18 electrons in the complex. This table is the one I took from the text. It basically shows the correct number of electron contributions from all the common ligands. And here I'd like you to pay attention to the common ones. Hydride, for example, chloride, hydroxide, cyanide, and then carbonyl, phosphine. And going down, there's carbene, ethylene. Going down, there's a nitrogen atom, and on the very bottom, there's a butadiene, cyclopentadienyl, benzene, and cycloheptatrienol. Okay. So for those ligands, you should know their correct number of contribution to the 18 electron rule. All right. So why those complexes follow 18 electron rule? The reason for the 18 is due to their electronic structure. So shown here is the molecular orbital diagram for organometallic compounds, and specifically this is for chromium hexacarbonyl. And you'll find the structure to be similar to what we have discussed in coordination complex. And basically you have T2G EG star level, and in this case carbonyl is a pi acceptor ligand, so you have empty pi orbitals on the top right, and the presence of those orbitals push down T2G. Now if you only consider a sigma ligand the interaction, then sigma donor interaction, then T2G will normally be a non-bonding orbital. But in the presence of pi star, pi acceptor levels, T2G levels were pushed down and become bonding. So, so this basically increases the separation between T2G, EG star, as we have learned before. But also what's more important is it makes T2G bonding. So it makes sense for the molecules to fill in as many electrons as possible into the T2G level, and fill in as smaller number of electrons as possible into the EG star level. So with this understanding, you can count how many electrons you can fill in. You can fill into the bonding orbitals, and you'll find that number is exactly 18. So 12 from the ligands and 6 from the metal in this case. The 6 mostly ligand character orbitals can accept 12, and the 3 T2G levels can accept 6. So that's a total of 18. Now, once you know the reason behind the 18 electron rule, you can also think about situations where this 18 electron rule does not apply. For example, if the ligand does not have any pi acceptor character, okay, and in those cases, the T2G level will remain as non-bonding. In that case, it does not matter as much to fill in exactly 6 electrons. The system may be just fine with 5 or 4 and even 3 electrons. Okay, and in another situation, if the EG star and the T2G level separation is pretty small, again, maybe because there is no pi acceptor level, or maybe there's even pi donor level. Okay, in those cases, the system would be probably also fine with putting electrons in the EG star level. So basically, this 18 electron rule, as I mentioned before, is empirical and it can be broken. And knowing the origin of this 18 electron rule, you would expect those rules to be more strictly observed in complexes having a strong pi acceptor characteristics. All right, so the 18 electron rules apply to the octahedral complexes. For square planar complexes, there's a similar rule, but instead of 18, we have a 16 electron rule here. The reason for the 16 electron rule is similar to the previous case in that it lies in the electronic structure. And shown here is the D4H ML4 complex MO diagram. And you notice that the largest gap in this complex is between the A1G and B1G. Okay, so in this case, if you count the number of electrons you can fill in, you'll find out that from the bottom up to A1G, you can fill in exactly 16 electrons. Okay, so the square planar complexes are mostly are most common for nickel, platinum, palladium, rhodium, iridium centers, and in those cases, you should expect 16 electron rule instead of 18 electron rule. All right, so now we're gonna briefly discuss carbonyl complexes. Carbonyl is probably the most common ligands for transition metals. Almost all, I believe, all transition metals can form a carbonyl complex one way or the other. And they can be made in a variety of different ways. You can have carbonyl react directly with metal. In such cases, the metal has to be divided into very fine particles to increase the reaction rate. You can also have a metal salt, such as chromium chloride, and reduce the salt and react with carbonyl in situ. This is basically can be viewed as a reduction of metal into very small particles. Those particles then got converted into metal carbonyl in situ. And finally, if you have carbonyl compounds to begin with, you can also induce thermal or by using photochemical process, some kind of decomposition, and that decomposition releases some of the carbonyl ligands and produce other kinds of carbonyl complexes. In a lot of the metal carbonyl complexes, the metal can be viewed as a zero oxidation state, and actually a lot of those complexes behave more like covalent compounds instead of ionic compounds. For example, iron carbonyl, pentacarbonyl, is a liquid at room temperature. It's very volatile actually. So in terms of bonding, carbonyl is a strong sigma donor and also a strong pi acceptor. So there are two kinds of interactions happening at the same time, shown on the bottom. For one, the carbonyl uses lone pair, which is located on the carbon side, to donate electron to the metal. At the same time, there's also pi interaction between the d orbitals and the pi star orbital of the carbonyl. And the interaction is is the donation of electron from metal to the carbonyl. Keep in mind, the pi star orbital of carbonyl is empty. Okay? So the overall interaction is the sigma bound electron density goes to the metal, and the d electrons density goes back to the pi star orbital of the carbonyl. Now, once you fill in electrons to the pi star orbital, you would expect a decrease in the bond order, because adding electrons to the antibonding orbital should decrease the bond order. So you can see this kind of effect in the IR spectrum of those carbonyl. You will see a change in IR vibrational frequency as a result of this back donation, which decreases the bond strength. So on the bottom, I showed a couple of IR vibrational data. One is for free carbonyl, and then you see typical monodentate donation to a metal center. So that'll give you a range of 1850 to about 2100. The more metal centers carbonyl interact with, the higher shift to the low wave number you will see. Okay, so for the mu3 triple bridging carbonyl, the vibrational frequency can be as low as 1600. On the right hand side, I show a couple of complexes, and you will notice that the higher electron density on the metal, the lower frequency of the carbonyl's vibration. Why is that? Because the higher density on the metal will make it easier to push electrons to the pi star level of the carbonyl, and that will result in a larger decrease in the bond strength, and a weaker bond will have a smaller vibrational frequency. The IR spectroscopy is a very powerful tool to analyze those carbonyl complexes. Upper side of this slide shows three examples of carbonyl complexes, and on the left is metal with 5 carbonyls. An example is iron pentacarbonyl. In this case, it is a D3H structure. You can count the number of electrons here. For example, let's say the metal is iron. So iron is column 8, and each carbonyl contributes 2. So that's 10 electrons from the ligand and 8 from the metal. So that's a total of 18. So it follows 18 electron rule here. In the middle is dicobalt and then 8 carbonyls. And those 8 carbonyls, 2 of them form bridging ligands, and the 6 others are monodentate. So there's additional cobalt-cobalt bond in this complex. So cobalt is column number 9, and each cobalt has 3 monodentate carbonyl, so that's 6. And then there are 2 carbonyls shared by the 2 cobalt atoms, and each bridging carbonyl contributes 1. So that's 6 plus 9 plus 2, so that's a total of 17 now. And then there's a cobalt-cobalt bond, so that's an additional 1 electron contribution, so that's a total of 18 again. Okay? And you can pause the video and run the numbers on the last iron 2 carbonyl 9 complex. Okay? Give yourself about a minute to run the numbers, and once you're done, you can resume the video. All right, so let's run the numbers together. So iron is column 8 again, so that's 8 electrons to begin with. And then there are 3 carbonyls for each, 3 monodentate carbonyls for each iron atom, and the 3 bridging carbonyls, so that's a total of 9. So 9 plus 8, so that's 17, and then there's iron-iron bond, and that contributes additional electron. So that's 17 plus 1, so that's 18. All right, so that's pretty much what I want to do today. Since we won't have a class on Wednesday, what I'm going to do is I'm going to post a couple of exercise problems on CourseWeb, and you can go over them on your own. And on Tuesday, I'm going to post the key, and on next Monday, we're going to continue our discussion in organometallic compounds. All right, thank you, and have a great holiday.